What's going on, everybody? It's Mr. Gus. I'm in the physics conference room. Today we're going to be discussing a little bit of right-hand rule stuff, and we'll be talking about what a single charge does in an electric field. So far in class we've discussed is the right-hand rule in terms of like a current carrying wire. So in this setup here, the picture behind me, I have got a battery attached to some wire, and the current is flowing in the direction you see here because of the orientation of the battery from the high potential to the low potential in the battery. It goes through. Now, I took part of this wire, and near the top of this, I've introduced a magnetic field. So maybe I've got a big magnet I'm holding above this wire, but I have a magnetic field only induced or only in this top part of the wire. So if I did this, what I would see, based on my right-hand rule, if I have a positive current, I'm following the positive charges around my circuit, I would have my thumb the direction of the current. My magnetic field, which is my fingers, is into the page. So I'm seeing my current go up, it goes around, it goes this way. So when my fingers are into the page like this, and my current is in the direction of my thumb, what I see is that this wire would experience a force all along it of the electromagnetic force, right? It would feel a magnetic force kind of pushing it up. And if I actually took this wire, I could see that, right? And we've seen a couple different demonstrations with a cathode ray deflecting a beam of charges, right? This is many charges all at once. Now, and the way we've described this is this equation, right? We've said the magnetic force is equal to my Bill sine theta, right? My B field times the current times the length of wire in that B field times sine theta, because we're looking for how perpendicular something is. But what we want to remember is that charge or current is just a measurement of speed of each charge, right? So current is also equal to charge per time, or charge per second. That's what the current really is measuring. A current amps is really coulombs per second. So I'm measuring this. So I can actually start making some kind of substitution. So let's go ahead and take our current and substitute this. So this goes in here, and I go FB equals my magnetic field times Q over T times length. The length of the wire really is the distance traveled, right? If this is the length of wire, that's the distance a charge travels, or charges travel through that magnetic field. So let's not call it L, let's go ahead and call it D, and then we'll keep our sine theta because we're still talking about the perpendicularity of the two values, okay? What I see here, when I rearrange some things, is that the magnetic field times, I'm going to flip these two because they're both in the numerator. I can move the distance value in. But I'm going to see distance over time times Q sine theta because it's the perpendicular thing. We can just keep using that. That's fine. But what do you know about distance and time? If I have distance over time for something moving in this way, what I'm really finding is that this is the speed of a charge. So I can rewrite this in a different way. I can say that the magnetic force felt by a charge in this field is equal to the magnetic field times the speed of that charge times the charge itself, sine theta, and again it's the perpendicular component of this between the B field and the direction it's moving in. This is a brand new equation, right? So if I don't need a wire of charge to go ahead and figure out the magnetic force on an object. All I really need is one single charge. I have a new equation. This new equation for tracking the single charge is that the force, the magnetic force felt by a charge in a magnetic field is equal to the speed of that charge times the charge itself times the magnetic field that it is experiencing or moving through. So this is a new way to calculate things, right? Force, I can calculate magnetic field. I could probably even calculate speed it moves through. I don't know if I know the force, the charge, and the magnetic field. But this is a new equation for a single charge in a magnetic field. Now, all that being said, let's look at what might happen to a single charge moving through a magnetic field. So come on over here. Let's assume I've got some kind of charged particle. I don't know, let's call it a proton for now. But I've got some positively charged particle. And of course, that's the direction of my right-hand rule. Let's use positive. I also have a magnetic field. Let's say that my magnetic field is into the page. It's uniform, like this, right? So this is my B field over here. That charge moves across the screen this way. My magnetic field is into the page. So it's going to experience a force. Now it's going to experience an initial force because if this thing is moving with this speed, as it enters the magnetic field, it's moving with a speed in that direction, but it's experiencing a force in this direction. And what we know about objects that move perpendicular to the force they experience is that they don't speed up or slow down, but they change direction. So let's go ahead and see what happens after this initial force, right? The initial deflecting force is going to deflect this charge upward. It's going to move forward, but change direction. So let's assume it's up here now. So now that it's been deflected, it's now moving in this direction, right? It's been deflected upward, changed the direction of its speed. Its speed didn't change, but the direction changed, which is why velocity changes. Deflects up. If this is the case, my thumb is still the direction of the charge, and my fingers are still into the page for the magnetic field. Which way is the force pointed now? The force is now pointed this way for my magnetic field, which means it's going to, again, deflect in that direction. So it deflects, it keeps kind of moving, but it deflects. Now it's moving upward. And what we see is force this way, FB. What we see is that this looks really familiar to a concept that we learned in our Physics 1 class, or our mechanics class, is that because velocity or speed and the force are perpendicular, we don't get a change in the value of the speed. Instead, we get a change in direction, and we start creating a circle. If you remember from your mechanics class, this is called the centripetal force because they are perpendicular. So it is net force, and net force is always mass times acceleration. In this case is equal what force is causing that circular motion. It's this magnetic force right here from the B field. But my acceleration, it's not changing the value of speed, so I can't use change in velocity over time. So instead, I have my centripetal acceleration, which, if you remember, is v squared over r. Is going to be equal to my point charge is force over here that we just came up with, which is the speed of that charge times the magnitude of that charge times the magnetic field it's entering in. And again, we see this drop out, that drop out. We're left with like mv over r is equal to the charge times the magnetic field. But this is a way we can go ahead and then solve for things. If I know the charge of a proton or the mass of the proton, based on the magnetic field, will dictate the size of that circle, and we'll look at some applications of that. But this is the basic understanding we need to have for a single charge moving through a magnetic field. If a single charge moves into a magnetic field, it will be deflected into a circular motion. Now, will it make a full circle? Depends on the size of the magnetic field and the size of the radius of that circle. But it will deflect into a circular path until it leaves that magnetic field. All right, and so we'll see some examples of this later. All right, until next time. See ya.